And now recording. Okay, so formal lecture will not be that long. As I said, Wednesday. Right, so we're here, flex day yesterday. So 4.9. So I'm just about on schedule, actually maybe a little bit ahead of schedule, so I can afford to stop earlier. Okay, again, 4.9 will not be on next Friday's exam. Okay, so again, coverage for the exam is 4.1 to 4.8. I'm just getting a head start on our last chapter. So 4.9 to 5.5, that'll be the last test. Okay, so I would lecture a little bit on 4.9, then stop and give you the quiz. Okay. All right, so here we go. So we're doing antiderivatives. A quick little review of what was going on with antiderivatives. So symbol integral of f of x dx is how you say it, integral of f of x dx. It means give a class of antiderivatives of a function. In general, you're going to put plus c for these problems. And I'll tell you when you don't put a plus c. In fact, I'll show you one example of that today. Okay. We do have the power rule, which is in reverse. So basically think of integration. And when I say integration, it means anti-differentiation. It's going backwards. Okay. You're basically going backwards. You're not saying, give me the derivative of this function or functions. You're saying, what functions are there whose derivative comes out to be that? And for almost all these problems, you need a plus c because you know the derivative of any constant is 0. All right, we have the power rule. Integral of x to the n is x to the n plus 1 over n plus 1 plus c. That's exactly the opposite of what you did when you differentiated, right? When you differentiate, you multiplied and subtract 1. So going backwards, you add 1 and divide. Okay, so I'll show you some more of those. Okay, now on page 352, they give you a table of antiderivatives, but in theory, you don't really need it. Because when you stop and think about it, here's a function, here's a particular antiderivative. It's just going backwards from what you already know. Okay, it's like saying, here are the functions, go this way for the derivative. Here are functions, go this way for the derivative. So it's almost like saying, if I go from right to left, that's a derivative. So now I'm going left to right, that's antiderivative. Right, so you see quickly on the table 1 over x, ln absolute value of x. Okay, the reason why it says particular antiderivative is technically if you want all the antiderivatives, you need plus c, but they figured out, okay, that's why they say particular antiderivative. We won't bother with the plus c. Okay, you do see the power rule there, x to the n plus 1 divided by n plus 1. E to the x, e to the x. Notice at the bottom there, cosine x, sine x. If you're going the antiderivative route, okay, careful, you're not going the derivative route, but antiderivative. Antiderivative of cosine is sine because derivative of sine is cosine. And take a look at this one. Again, it's backwards. Suppose I ask, what's the derivative of b to the x? And that's fair game for the next exam. That'll be b to the x times ln b, right? So you multiply by ln b. So guess what happens when you anti-differentiate? You divide by ln b. Very logical. Right? And quickly look at this. I hope you don't get thrown off by this. Integral of sine is negative cosine. Again, careful, not the derivative, antiderivative. Okay? Or another way of saying is, what's the derivative of negative cosine, positive sine? Secant squared tangent, because the derivative of tangent is secant squared. Secant tangent, secant, because the derivative of secant is secant tangent. Okay. 1 over radical 1 minus x squared, inverse sine. 1 over 1 plus x squared, inverse tangent. And since cos and sinh are derivatives of each other, they're also integrals of each other. Okay. All right. So it's there, you know, don't look at it that carefully until after the test, although, you know, it's never wrong to look at it, I suppose. Okay, so a few problems from 4.9, and then I won't go that long, and then I'll stop. Okay, integral of 1 plus t squared over radical t dt. Okay, and the first thing I might mention is for integrals, there's no such thing as a product rule. There's no such thing as a quotient rule. Okay, so you look at this and say, oh, there's a quotient. Let me do the quotient rule. There is no quotient rule. There is no product rule. In fact, one of the major topics of Calc 2 is how do you integrate with products and quotients. Now for derivatives, it'll always work, right? Say, oh, I have a function times another function. I always know what to do, right? First times derivative of second, plus the second times derivative of first. If I have a quotient, something divided by something, I know what to do. Bottom times derivative of the top, minus the top times derivative of the bottom, all over the square of the denominator, right? That doesn't work for integrals. There's no general rule for products and quotients of integrals. Okay, so we have to do other stuff. So what do I do here? All I do is just divide, divide them all by radical t. 1 divided by radical t, t to the negative half. T divided by radical t, that's t to the 1 divided by t to the half is t to the half. And t squared divided by t to the half, 2 minus a half is 3 halves. Okay, so that's how you should do this particular one. Okay, and now the power rule. Add 1 divided by the new exponent. Add 1, t to the 1 half divided by 1 half. T to the 3 halves divided by 3 halves. T to the 5 halves divided by 5 halves. Okay. And you know, when you divide by a fraction, you multiply by the reciprocal. So once we get going with this, I'm normally not going to write this step. I will immediately multiply by the reciprocal, right? So I say to myself, I know I'm dividing by a half. That's the same as multiplying by 2. And the normal way to write t to the half is radical t. So you should do that. Okay. And dividing by 3 halves means multiplying by 2/3. Dividing by 5 halves means multiplied by 2/5. And there we go. Okay. In other words, you're all good in arithmetic because you're taking calculus. I will go straight from here to here in general. In other words, t to the 5 halves, and then I say divided by 5 halves. Okay, if I divide by 5 halves, it's the same as multiplying by 2/5. Okay, that should not be that big of a jump. Okay. All right, 19. Integral of 2 to the x plus 4 sinh x. Okay, so integrate 2 to the x. Okay, what does integrate? Anti-differentiate. So careful, when you see this funny s, okay, you're asking for antiderivative. What does the dx do right now? It doesn't do anything except name the variable, but it does become important toward the end of our semester, but in terms of changing variables, we'll worry about it then. All right, what was the derivative of 2 to the x? It was 2 to the x times ln2, right? So you had to multiply by an ln2. So what happens when I differentiate? I don't multiply by ln2, divide by ln2, right? Because they're opposite operations. So think of integration and differentiation are opposite operations, just like adding 5 and subtracting 5 are opposite operations, or cube root and cube, right? Or multiply by 7, divide by 7. So integration, differentiation, they're opposites. So 2 to the x ln2, and the integral of 4 sinh x is 4 cos x, and then plus c. So that's my answer. Remember, you can always check your answer by differentiation. What is the derivative of this? So if I differentiate this, 2 to the x over ln2, the coefficient is 1 over ln2. That wouldn't change. So it'd still be 2 to the x ln2 times natural log of 2. That natural log of 2 cancels out that natural log of 2, and you get that. Derivative of that is that, and the derivative of any constant is 0. Okay, and I was only going to do one more, then I'll let you have the rest of the time for the quiz. Okay, finding c. So far, all of these have had a plus c, but in some cases, you can find a c. That would be like problem 23. So when you see something extra, like in 23, see where it says f of 0 equals 4 for 23. Now, if you didn't have that, if it just showed you this, it'd be the blah, blah, blah plus c. When it shows something extra like f of 0 equals 4, you're going to be able to solve for c. Okay, that's true for the ones that I'll show you starting Monday. See, like, I don't know, 33, f of 1 equals 0, or, you know, f of 8 equals 21 for 35 and so on. You'll be able to solve for c. So how do you solve for c? So f of x equals 5x to the 4th minus 2x to the 5th, capital F of 0 equals 4. Okay, so first I do the blah, blah, blah plus c as usual. So integral of 5x to the 4th minus 2x to the 5th dx. Okay, power rule. 5x to the 5th over 5 minus 2x to the 6th over 6 plus a constant. Simplify, that's x to the 5th. 2 6 1/3, so negative 1/3 x to the 6th plus c. That's capital F of x. Quick double check. If this is the correct antiderivative integral, then the derivative of this should be that. Let's check. What's the derivative of x to the fifth? 5x to the fourth. What's the derivative of this? 6 times -1/3 is -2 x to the fifth. It works. And of course, the derivative of any constant is 0, so we're good. So that's it. If I didn't see that f of 0 equals 4. Now, in this case, when they show you this stuff, you can solve for c, because f of 0 equals 4 means plug in 0 for x, and the answer comes out to be 4. So 4 is y, 0 is x. If you ever forget, normally we do f of x, right? We don't almost never we do f of y. This is f of x. So put a 0 right here and here. That's easy, right? 0 to the fifth is 0. 1/3, 0 to 6 is 0. Plus c, that comes out to be 4. So that's 0 plus c. So c is equal to 4. So now in this case, instead of blah, blah, blah plus c, final answer is x to the fifth minus 1/3 x to the sixth plus 4. Okay, so it's not an infinite class of functions. It's only one function, one and only function. Okay, that one and only function has two properties. The derivative is this, right? We just checked that, that works. Derivative of x to the fifth, 5x to the fourth. Derivative of -1/3 x to the sixth, 6 times -1/3 is -2 x to the fifth, and the derivative of any constant is 0. Okay, that satisfies the first property. Okay, but now we have this extra property. Second property, when I plug in 0, I get 4. That's true. Plug in 0, 0 plus 4, you get 4. And we're finished. Okay, and that was all I was going to do for today, folks. I will continue lecture on Monday, but let me check to see. No, so people just join. Okay, I got you. Okay, any other questions? Otherwise, I'll go straight to the quiz. I want you to have the rest of the time to do the one problem, applied max min problem. Any questions, please? Okay, we'll go straight to the quiz. So get your cell phones ready or be ready to do a screenshot. It's just one problem, but like last week, it might be fairly involved. Okay, I'll leave it like this to see the whole thing, but I'll try to raise it up. Okay, a farmer needs to have 600 square feet of fencing. The fence is to be shaped in a rectangle with an extra fence in the middle to have 2 pens. See the figure below. So we had a homework problem that was sort of just like that. Okay, find the dimensions that would minimize the amount of fencing needed. Okay, so I've given you x, 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 and 2 y's. The area, therefore, is length times width, or x times y. So area is 600, which is xy. An expression for the fencing is pretty much right there. I mean, I've got all the letters there, right? So how many x's and how many y's are there, right? So you work on that. I'll go ahead and give you some hints now. So your expression for the fencing involves x and y. How many x's are there? How many y's are there? I've shown it to you pretty much. Okay, but you need to eliminate a variable. So can you see how you can eliminate y? Hint is look at the area, right? Area is 600. 600 equals x times y. Can you solve that for y? Right? Solve for y and then plug it into the expression for the fencing, and then do your minimization after that. Okay, you need to do a first derivative and a second derivative in order to get this going. Okay, so I'm going to assume everybody has this now, either a screenshot or on your cell phone. So get started and stop to share, set up your breakout rooms. I'm also going to stop recording.